Section 4.3 and 4.4, they are all about what derivatives can tell us about the graphing of the functions. These two sections, we can see the derivatives can be used to explain the behavior of the graph, such as we can find the intervals of increase, decrease. We can identify the local max, local min. Also, we look at the first derivative, second derivative to explain more about the behavior of the graph. Increasing and decreasing function. For the function f of x on the interval I, f is increasing if the function value at x2 greater than the function value at x1, where x2 is greater than x1. For f of x that is decreasing on the interval I, the function value at x2 less than the function value at x1, where x1 is less than x2. We can use a derivative to explain about the increasing and decreasing behavior. If the f prime is greater than 0, the function is increasing on the interval I. If the f prime is less than 0, the function is decreasing on the interval I. As you recall, the f prime is the slope of the tangent line. If the slope is negative, the graph is decreasing. Slope positive, the graph is increasing. Recall how to find the critical points or the critical values. We are going to find the derivative and solve for x where f prime or the derivative is 0 or the case that f prime is undefined. The critical points can tell us either the possible x there is the local max, local min, or is not local max, local min, or the point of undefined of the function. If you have the graph, it's not too bad to explain whether the function has local max or local min or the absolute max, absolute min as shown on the graph here. But we are going to use the derivative test or the first derivative test to identify the local max and local min of the graph of the function f that's provided. Suppose f is continuous on an interval and contains a critical point c. And how to find the critical point c? We find the derivative and look for the x or the c that's f prime 0 or f prime undefined. Assume f is differentiable on an interval containing c, except for the c itself. If the sign of the f prime changing from positive to negative, that means the graph contains the local maximum at the point C. For the derivative, changing the sign from negative to positive or from decreasing to increasing, the graph contains the local minimum at the point C. In the case that the sign of the f prime doesn't change, that means the f doesn't have local max or local min at the point C. Absolute extreme values on any interval. If there is one local extreme values, either one local max or local min, it implies that there is only one absolute max and absolute min and also the same absolute max, absolute min. Suppose the f is continuous on an interval I and contain one local extreme value at point C. If local max occurs at C, then that local max is the same as the absolute max. Similarly, if a local min occurs at C, then the f prime at C is also the absolute min of the function on the interval I. Inflection points. To find the inflection point, we starting with finding the second derivative. Look for the case that the second derivative of the f equals 0, and the other case, the second derivative is undefined. Since we look for the inflection points, by definition, the inflection point is a point that the graph changing from concave up to concave down. To identify concave up, concave down as the derivative or the slope changing in a positive way or in a negative way. So we use the derivative of the derivative, which is the second derivative. The second derivative of the function greater than 0, that means the slope is increasing. Therefore, the function concave up. For the second derivative that is less than 0, that means the rate of change of the slope is decreasing. So the slope of the graph is decreasing in a quantity y. So the f is concave down on the interval I. If f is continuous at c, if changes the concavity at C, changing from concave up to concave down or concave down to concave up. The other way we say if the sign of the second derivative changing from positive to negative or from negative to positive, the point C is called inflection point. The test for concavity. Suppose the second derivative exists on an interval I. The second derivative greater than 0, then the function concave up. Second derivative less than 0, the function concave down. If C is the point of the I at which the f double prime changes the sign, so f has an inflection point at the point C. Next, second derivative test. The second derivative test for local extrema. Suppose the second derivative is continuous on an open interval I containing C with the f prime at C equals 0. Recall f prime at C is equals 0 tells us the C is a critical point. So if the second derivative is positive, or basically C contains in the interval that concave up, f has a local minimum at C. For the second derivative at the point C less than 0, or C contains in the interval of concave down, the function f has a local maximum at the point C. The f double prime equals 0. That means the sign or the rate of change of the slope is not zero, is 0. So then the test is inconclusive. Inconclusive. So that means f may or may not have the local max, local min. In summary, for the sign of the second derivative, if the second derivative is positive, we use the iconic smiley face, so it's concave up. If negative, not happy face, so concave down. For the case that we use the second derivative test, so the second derivative tells us either concave up or concave down within that interval that containing C. If the interval of concave up, which is the second derivative greater than 0, the point C contains in a concave up, so the point C is the local minimum point. And the other way, if the second derivative is less than 0, so that concave down, that means it's not happy. So the point C that contains in the unhappy interval here is the local maximum point.